second derivative and beyond. So we have our notation for our first derivative, which was in Newton's notation, just one dash. So he has a second derivative, puts two dashes. The third derivative, three dashes. Eventually, you get tired of putting dashes, so eventually they would be like, oh, there's the fourth derivative. We'll put a little 4 up there, so we don't have to write too many dashes, especially if we want to find the 41st derivative. That would be a lot of little dashes that you'd have to make. So, but for the most part, we don't really go beyond the second one. The second one is an important one. After that, there's really not that much application. There's a lot of applications that come up with the first derivative and the second derivative, but not much beyond that. So if you had y, you could put a second dash. And if you had Leibniz notation, you could put 2's in there, meaning you've done something twice. But the 2's are kind of in a weird spot. There's a 2 in between the d and the y, and there's a 2 after the x. Now, technically, why there are 2 of them can be thought of this way. You know when we do the derivative and we do this notation? That says take the derivative. If you took the derivative again, you'd have another d, and you'd have another dx. So the reason the 2 is in front of the y is because d times d, the d happens twice. This is your y. Your y is only there once. So the d2y is because the d happens twice. And technically, the dx probably should have brackets around it, because the dx squared is really that dx times dx. It's not just the x that has been squared. But mathematicians don't like brackets in their final notations. So I think it was just a matter of, okay, if everybody's okay that we don't put brackets there, even though it means the dx has happened twice, we'll just go with that. And they're like, okay, we'll do that. That's okay. So technically, in proper mathematical notation, this probably should have showed up like this. But they just have d2y by dx squared. And this is Leibniz notation. So if you wanted to find the second derivative, well, you just have to find the first derivative. And then once you found the first derivative, find the derivative of that, and you have the second derivative. So second derivative questions will be nothing new mathematically other than new notation and having to do a derivative after you've done the derivative once already. Not really anything crazy as far as our mathematics go. Like we have no new rules. Implicit differentiation, which was, I think, difficult. Now we're straightforward. Okay? Unless you had to find a second derivative of one that was implicit differentiation to begin with. That could be quite complicated. But let's start off here. You've got f of x. I look at f of x and I decide at first I'm going to change my f of x into notation that lets me take derivatives easily. The first derivative then is nice. The 3 comes out in front, subtract 1 from the exponent. The negative 1 comes out in front, subtract 1 from the exponent. And this is nice, because now it's still in a good form to do the derivative again. So then our second derivative, here the 2 would come out in front, subtract 1 from the exponent. The negative 2 would come out in front, subtract 1 from the exponent. So the second derivative is just an excuse to make you do the derivative twice. what do we see initially? We see a chain rule. You do have an option. You could multiply it out completely and then just have your regular power rule. But that doesn't look like a fun one to multiply out completely. So I will look at my chain rule. My chain rule says, do the derivative of your outside function. Well, the outside function is a 3, so the 3 would come out in front. Subtract 1 from the exponent, and keep the inside the same. Then multiply by the derivative of the inside function. Now we have to do the derivative again. Either A, you can multiply it all out, or do you see that you have a product rule and a chain rule? So I'm going to find my second derivative now. I have two things multiplied by each other. So product rule says keep one the same, multiply by the derivative of the second one, plus keep the second one the same, multiply by the derivative of the first one, and the first one is a chain rule. Outside function is the square, so this 2 comes out in front. Subtract 1 from the exponent. Keep the inside the same. Multiply by the derivative of the inside function. And this would be the second derivative. Now, had we multiplied it out, x squared minus 3x, x squared minus 3x, x squared minus 3x. Can you see that you would have had an x to the 6th plus dot, dot, dot. All the way down, and the very last one would be minus 3x, minus 3x, minus 3x, minus 27x cubed. With a bunch of other stuff in between, if we multiplied it all out. If we kept going with the derivative, okay, I can tell you this one wasn't bad, this one was worse. Can you see that you would have a product rule, a triple product rule almost here? Unless you put the 2x minus 3's together to get a 2x minus 3 squared, then you would have a product rule with another chain rule. If you kept going, let's go to here. I'm going to tell you this is actually an easier question than the previous ones. Initially, it seems a lot harder, because initially, to figure out the 7th derivative, you'd have to find the first one, then find the second one, then find the third one, then the fourth one, then the fifth one, then the sixth one, and finally the 7th one. But if I just imagine it multiplied out like this, can you see that after 3, the first derivative will make this down to an x squared. Then it'll be down to an x. Then it will be down to a number. And the next time, a number would be 0. So the first time you do a derivative, this has an x to the 5, an x to the 4, an x to the 3, an x to the 2, an x to the 1. Eventually, it'll have no x's. And I'm pretty sure by the 7th one, we're down to 0. Does that mathematically work for us? Did I count the right amount? First derivative have it x to the 5, second x to the 4, third x to the 3, fourth x squared, fifth x to the 1. 6 would just be a number. Be the 6th one. 6 times 5 times 4 times 3 times 2 times 1, because the 6 would come out in front. Next time the 5 would come out in front. Next time the 4 would come out in front. Next time the 3 would come out in front. So you would get 6 times 5 times 4 times 3 times 2 times 1. That's kind of fascinating. So we can sometimes see interesting patterns later on in a derivative. everything would go away. If we look at the first one we did, if we kept going, the negative part keeps going. This one will eventually go away to be 0. But the negative one, which, because you keep subtracting 1, would keep on going. All right. Let us just, do you have your textbooks with you? 10 minutes to try some. And then we will keep going.